Hello students, welcome back to this new session. In this session, I am starting with the theorem, that is Cauchy's theorem, which is one of the important theorems of your syllabus. Okay, so let us first understand and prove this. Okay, so the statement says, if f of z is analytic at all the points inside and on the closed curve C, then the line integral over the closed curve C, f of z dz is equals to 0. So means what? If you are having, say this is x-axis and this is y-axis and you have the origin and you have a simple closed curve C on this. Okay, where your function f of z is analytic at each and every point inside the closed curve C and also on the boundary of the closed curve C. On the boundary as well as inside, the function f of z is analytic. Then the integral over this closed curve C, f of z dz is equal to 0. This is what Cauchy's theorem says. Now let us prove it. Proof. Let f of z is equals to u plus iv. That is the real part plus the imaginary part. Then integration over the curve C, f of z dz will be equal to integration over the curve C, u plus iv into dx plus I dy. Now why I am writing dx plus I dy here? Because you know you take your z as x plus iy. So what will be dz? I'll make a partition here. dz will be dx plus I dy. Is it not? So this value for dz will be dx plus I dy, and we know that f of z we have taken it as u plus iv. Okay, now let us try to separate the real and imaginary parts here. So it is integration over the curve C, u into dx gives you the real part. Okay, and if you multiply the imaginary part with the imaginary part, you get the real part, which is I into I square is -1, so minus v dy, okay, plus I v dx plus I u dy. You get it something like this. Now I would like to separate the real and imaginary parts. It will be under integral sign C. Okay, u dx minus v dy is the real part, plus I can take I, okay, common. Integration over the curve C, I am separating it now. So you have v dx plus u dy. Okay. So integration over the curve C, f of z dz reduces to this form. Okay. Now call this as equation 1. Call this as equation 1. So you'll have learnt Green's theorem in a plane in second semester. I hope you all remember that, but even if you have not remembered, I'll just give you the the statement and what it says. We are going to apply that theorem here, Green's theorem in a plane, because this entire thing we are doing in a plane, xy plane. So that same thing I can apply it here. So we have Green's theorem in a plane stating that if m of xy and n of xy are two real valued functions having continuous first order derivatives. First order, I would say not derivatives, it should be partial derivatives. Having first order continuous partial derivatives in the region R, enclosed by the curve C, enclosed by the curve C. That is, if you are having a closed curve C and you are having m of xy and n of xy both defined and they are having continuous first order partial derivatives in this region R, which is enclosed by the closed curve C, then what it says, integration over the curve C, m dx plus n dy, m dx plus n dy is equal to double integral over the region R, dou n by dou x minus dou m by dou y dx dy. This is the Green's theorem in a plane. So what it says, if you are having two real valued functions m of xy and n of xy in such a way that they are real valued functions of continuous first order partial derivatives defined in the region R enclosed by the closed curve C, then by Green's theorem we have integration over the curve C, m dx plus n dy. M is the first function, n is the second function. M dx plus n dy is equal to, you are going to take n, differentiate it with respect to x, the one which is the coefficient of dy, differentiate it with respect to x partially, the one which is the coefficient of dx, differentiate it with respect to y partially, take the difference between the two, take double integrals over the region R, dx dy. So that is, it's connecting the line integral to double integrals, okay, yes, over the region R. This is what the Green's theorem says. I am going to call this as equation 2. So I will use this in each of the integrals of equation 1. Okay. Using this in the right hand side of equation 1. So to both the integrals I have u dx minus v dy and v dx plus u dy, the two integrals I have. To both the integrals I'll make use of this Green's theorem. So what will happen to my integration over the curve C f of z dz? It will be equal to double integration over the region R. Look at that equation 1 and look at the first integral of that equation 1. So the one which is the coefficient of dy must be differentiated with respect to x. So we get minus dou v by dou x, because in place of n, see, just compare it with this. In place of n, you have got minus v. So I can take that minus v outside. Dou v by dou x minus, in place of m, you have got u. Okay. So minus dou u by dou y. Like this you get. Yes. Dx dy. You are done applying the Green's theorem for the first part of this integral. Okay. Plus I double integration over the region R again. Now let us apply the same Green's theorem for the second part of this equation. So the second part says it is v dx plus u dy. In place of n, you have got u. So it will be dou u by dou x. Coefficient of dy is u. So it will be dou u by dou x, because it is dou n by dou x over here, minus, now the coefficient of dx is v here, like how it is m over here. So it will be minus dou v by dou y, dou m by dou y. So that's been replaced by dou v by dou y, because in place of m we have got v, dx dy. This is what you get. Okay. Now since f of z is analytic, dou u by dou x, it must satisfy the CR equations, is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. What you say? Right? So this implies the first part of this integral, see, the two of them are equal, right? So minus dou v by dou x is equal to dou u by dou y, right? So this will be, if you take the difference between the two, it will be 0. Similarly, since these two are equal, the difference between the two will also be 0. This implies integration of the curve C, f of z dz will be equal to So the two brackets are turning 0 because the function f of z is analytic, and since it is analytic, u and v must satisfy the CR equations, and according to the CR equations we have this. So each of the bracket is turning 0. Therefore, the integration over the curve C f of z dz is equal to 0. This is the complete proof of your Cauchy's theorem. Okay. Now let us continue with the derivation for Cauchy's integral formula. But before that, I will just give you small things that are required for Cauchy's integral formula that comes arise. I mean that is actually we have got through Cauchy's theorem only. We have certain consequences that we have to use in Cauchy's integral formula. That we'll discuss first. Then we'll go to Cauchy's integral formula. Let's continue with that now. Now let us discuss the first consequence of Cauchy's theorem. It states that if f of z is analytic in the region R and if there are points P and Q in it, then integration from P to Q f of z dz is independent of the path joining P and Q. So what it says, see here, if you are having a function f of z defined in an xy plane like this. So you have a region R enclosed by a closed curve C, say this is the region R, okay, and there are some, I'll not write this R over here, so it's a region R over here. There are points P and Q here, okay. So the integration between P and Q f of z dz is independent of the path. Means if you take the integral from P to Q f of z dz, it is independent of the path. You can join this way or this way. Wherever you take the path, the value of this integral will not change, okay. You follow any path, the value of that integral will be same. So yes, this is just the consequence. Proof and all is not there in your syllabus, but I'll just give you a small hint how to prove it. See, just we'll discuss it and keep it so that it will not be a problem. So I'll once again take the 2 points P and Q separately here. See, I can join this says by the curve C1, okay. I can also join it by the same another curve, say C2, okay. Now this C1 plus C2 from P to Q minus C2, yes or no? Look at this. C1 is also the curve joining P and Q. C2 is also the curve joining P and Q. From P to Q only it is. Look at the direction. Okay. So integration, I'll call addition of say let the C be the curve C1 plus of minus C2 I will say. Look at this. From C1 to minus C2. Minus C2 will be this. If C2 is this way joining P and Q, minus C2 will be in opposite direction from Q to P. Okay. So let C be a curve. Addition of C1 plus of minus C2 I will take. So that integration over the curve C f of z dz. Now this is a closed curve. If you are starting with P, you are starting with P from C1. Yes, C1 is joining the curve P and Q, right? C2 is also the curve joining P and Q. But what is minus C2? It is the curve joining Q and P, right? So what is my C? I am saying C1, C is C1 plus minus of C2. Okay. So C1 you start with P to Q again from minus C2 means from Q to P. So it's a closed curve. C is a closed curve. So according to Cauchy's theorem, for a simple closed curve C where f of z is analytic, inside and on the boundary of that curve, integration over the curve C is 0. So according to that, if it is 0, then I must have integration, but C is the combination of C1 and minus C2. So integration over the curve C1 f of z dz plus integration over minus C2 f of z dz is equal to 0 you get. But you have learned this one property of line integrals. Integration over C1 f of z dz. Now this minus sign can be brought here and kept it as minus of C2 f of z dz. This is equal to 0. Now I can bring this to the left hand side, right? So the right hand side, okay, I can write it like this. Look at this. This by the property of line integrals. In the first part of this first class of the module 2, I have already given this property. Integration over minus C is always equal to integration minus C. Yes, integration over minus c is equal to minus integral c. This is already there. So according to that, I can change the minus sign over here and bring it to the right hand side. So that integration along the curve C1 is equal to integration along the curve C2. What are C1 and C2? They are two different paths joining the point P and Q. Yes, so therefore the integration of f of z is independent of the path. Hence we have proved it. There is another consequence that is also very important. Let us discuss even that. Now let us discuss the other consequence, which is also a very important while we are deriving the Cauchy's integral formula. It says what? If there are two curves, say C1 and C2, the two are simple and closed curves such that C2 lies entirely within C1. You can see that in the figure. I have drawn it for you. See, this is the curve C2. This is the curve C2 from Q to T to U and again Q. Okay. This is the curve C2. Okay. First I will not consider this. Okay. Let us first only consider the curves. See, look at this curve C2. I hope this is seen like this. Its direction is like this, in clockwise direction. Okay. Whereas C1 is in anti-clockwise direction I am taking. Okay. Look at this. C1 is like this. Okay. Now, irrespective of directions, for now I have just taken the directions, or I'll just can erase everything for you and redraw it once again for you. Look at this. Say this is C1, the curve C1, boundary C1 I should say, and there is inside that there is another boundary, say C2. Okay, then integration over the curve C2, and what is being said about f of z? F of z is analytic on C1 and C2 first, and also in the region between C1 and C2. First of all, the function f of z is analytic on C1 and C2, and also in the region between, that is the annular region between C1 and C2. Then integration along C1 f of z dz will be equal to integration along C2 f of z dz. So the proof and all is not necessary, but I'll just give you a small hint. It's very easy to prove this. What we'll do, we'll make a small joining between the two curves here. Okay, a small cut. Okay, let this point be P on curve C1. And on curve C2, let there be another point Q which is joining that P. Okay, like this. Okay, now I'll take the directions for C1. Let the C1 be moving like this. Okay, and C2 be like this. Okay, so you can see C1 is going in anti-clockwise direction, where C2 is going as in clockwise direction. This is anti-clockwise direction. You can say that. Okay. So now I am taking the points, arbitrary points on curve C1, say R and S, and say this is T on C2 and U on C2. Okay. So I have a closed curve here. How I'll start my closed curve C? I'll start my closed curve C as P. Let C be made up of the paths like this. Look at this. Let C be a curve as connecting P, R. See, from P to R, then S, then again P to Q. Okay, PQ. Then I'll go to T, then U. Okay, then Q, then P, then P. So now I can make a partition of it. How? Look at this. First this complete. Okay, P R S P, it is C1. Okay, and again from P to Q, it's a single line like this. I'll keep it aside. Now from Q T U Q, this is but C2 for me, is it not? This is but C2. Then again QP is again a line segment. Is again a line segment over here, right? Yes. So now just see. It's a closed curve. You're starting with P and you're ending with P. Is it not a closed curve now? Yes. Is a closed curve. So now since it is closed curve, integration over curve C f of z dz must be 0. according to Cauchy's theorem, because f of z is analytic everywhere and on the boundary of that curve C, because whatever we are considering, all the boundaries, everywhere the function is analytic. So according to Cauchy's theorem, this integration should be 0. This is our curve C. Okay, now I have done the partitions already for you. So this thing I can rewrite. The LHS of this thing I can write it as integration along C1 f of z dz plus integration along PQ, because look at this, I have done the partitions properly for my curve C. Okay, integration along PQ f of z dz, then from PQ to integration along C2 f of z dz, because that is C2 for me. Look at that, Q T U Q, right? So it is C2, then plus integration along QP f of z dz is equals to 0. Okay, now actually the direction for C1 I have taken in this way. So even C2 should also be taken in that way, but it is not been taken, so I have to take a minus sign over here. C2 should also move in this direction only. So I have to take minus C2 for that. This is actually minus C2. Okay, so therefore our path is like that. Okay, now C2 is minus, so therefore integration along C1 f of z dz. Now PQ and QP, they are the integration along the same line segment. One is going from P to Q, another is going from Q to P. They will get cancelled, or I can rewrite like this. Look at this, f of z dz plus, okay, because of again the properties of integrals, I can write it like this once again. And again by the properties of integrals, I can write like this as well. Look at this, dz is equal to 0. Now these two will get cancelled. Okay, and you will have this integration along C1 f of z dz minus integration along C2 f of z dz is equal to 0, or integration along C1 f of z dz is equal to integration along C2 f of z dz. Okay, so just you have to remember, whenever the function is defined on the boundary and on the annular region of the two curves, okay, like this, if suppose two curves are in such a way that one curve is lying entirely on the other curve, inside the other curve, then and also the function f of z is analytic inside the region between the curves and also on the boundary of the curves, then integration along first curve is always equal to the integration along the second curve. This you have to remember. Okay, this is one of the consequences of Cauchy's theorem. Now let us continue in my next session about Cauchy's integral formula. There we'll learn how to derive it and then we'll solve certain problems based on that. Okay, till then, thank you.